So we did start doing some review for functions. Today is about the domain. Domain of a function we denoted by dom, E-O-M-F. Of a function is basically a fancy word for all possible inputs for that function. So set of all possible inputs for a function, for the function f. So this machine, what kind of numbers we can put in? You remember that domain of f, well, usually in calculus, we work with functions whose input is numbers, real numbers. So you get a subset of R with some conditions on X, so acceptable inputs. So the conditions that define this. You have to be able to write the domain in the set notation, which is this guy. Also in the interval notation. So also I will write it as interval notation. For this course, starting with, we have two restrictions that we have to apply when we're trying to find domains. The one is, well, these are the mathematical restrictions or conditions. This comes from the basic fact. You can divide any number to any other number but 0. So the denominator cannot be 0. So when you have a function whose definition involves a denominator fraction, the denominator cannot be 0. And that's the restriction that defines the domain. The other one, which is less problematic, because in the higher advanced math, you kind of resolve it by introducing so-called complex numbers. And this says that the negative numbers have no even root. So in other words, under the square root, if you have a square root, under the square root must be always bigger than or equal to 0. The first condition is a big no. This is very important. No matter how advanced your math is, you cannot divide a number by 0. 0 does not have inverse. But the second condition, which is important for us because we are working with real numbers, can be resolved in higher math. There are other conditions that will come out, other restrictions will introduce as we go on. So one of them is when you have log function and trig inverse function, that's where you will see that, oh, there are new conditions that you have to apply when you work with the domain of functions. Well, let me apply. Is there any questions, any comments? Yes, Vilo, please.
Would you mind scrolling up just a bit, just so I could see that first part one more time?
Are you good now?
When after you record the videos, are you going to post them somewhere? Because I couldn't find them on OWL.
Yes, I did actually post. The last week's class was recorded, and if you go to the tab called tutorial sections, there is a subpage for our section and other sections, the sections that I teach, 006 and 007. If you click on that, you will see that week 1, it has a video link there, also the PDF file of this video. Whatever I'm writing, I will post it there. Well, sometimes I will post the video I recorded in the other section, but I will post only one of them. They're very similar, and you sometimes can add comments. I will try to do always add a comment tool there so that you can add comments if you can have discussions there. Please go ahead and use that one. Okay, so back to the work. We have rational function. Rational function is when you have a polynomial divided by another polynomial. So any function whose definition involves a fraction has a denominator, the domain of that function will be all real numbers, but the ones which makes the denominator 0. So I want to exclude the points which make the denominator 0. So I want to try to find what are the values of x for which this guy is equal to 0. So I will exclude it. Solving not equal is very similar to solving equal. So solving that kind of inequalities are very similar. So you basically do what? So here I want to find two numbers. This is quadratic, easy to solve. I want to find two numbers which add up to -3. And when you multiply, you get +2, which is this guy. So two things multiply and gets 0. It means that either this one is 0 or the other one is 0. And that means that this is x must be equal to 1 or must be equal to 2. These are two values which will make the denominator 0. We are interested in cases that these are not 0. This will go exactly the same way. The only thing is that, well, at the end, you have to, instead of saying either x is 1 or 2, you have to say x must not be 1 and should not be 2. This is the domain of that guy. Well, I need to write this one in terms of also in the interval format. Well, this is something that you have to now start working and be able to use, especially in the web work quizzes. You have to be able to input functions in, sorry, the sets in the interval format, most of the cases. So if you look at this set, you will notice that, oh, we are going to include everything but these 2 points. In terms of intervals, that means that I need to go from -∞ up to 0.1. I should not include, because when it is included in the interval notation, we put square bracket. When you don't want to include that endpoint here, which is 1, I don't want to include it because that's one of the points I excluded. So that's when we use a round bracket. So exclude, include. And then union, go from 1 to 2. I'm not including the endpoints, then go from 2 to plus infinity. And you have to be able to
Wait.
do that one. Yes.
Sorry, which notation is that?
This is interval notation.
The bottom one or the top one?
Oh no, bottom one is I'm just showing you what does it mean on the real line.
Right, okay.
I found out that's showing that real line set is always helpful for you to think of intervals, but this is interval.
Okay. And then what's the format above that?
Oh, this is called set notation.
Set notation. Thank you.
Or at least I call it. Well, for mathematician, both of them are sets, but we are talking about practicality of what we are doing here. For the other one, we see that, oh, there is there is a square root. Well, even if this was like fourth or eighth or 12th, whatever even root, you have to remember that in the real world, domain of functions which involve even roots are the points which makes the denominator non-negative or just positive. Now, I want to find points which will give us this property. There are more than one way to solve this, especially for this specifically, because this is a linear inequality. For the linear inequality, what I do, I can try to do this one very similar to the equality. So this is like that. I want to take 2x to the other side, negative 2x to the other side turns to 2x. Then multiply everything by 1/2. This will be x. The inequalities like this work very nicely. The linear ones works very nicely as the equality. There's only one thing that you have to be careful. If when you're doing multiplying both sides of an inequality by a negative number, only negative number, you have to flip the inequality. Well, let me show you the other way of solving that. I could have done this way. I could have taken 1 to the other side. It will turn to -1. But then I multiply both sides by -1/2. If you multiply an inequality by a negative sign, you have to flip the inequality. That's the rule. And then this means that x is less than equal to half. Well, the same numbers, yes, that's the same. This works when you have linear inequality. In general, the way you need to work is what's called sine table. Sine table is that when you have an expression, you have to find wherever each part of this guy makes it 0. In this case, this is just solving this very simple equality. Then you say that, okay, see, x can go from -1/2 to half, then to positive. At 1 minus 2x, at half, it is 0. I have to find out where it is 0 because 0 is not interested. We are not interested in 0. We are interested in where it is positive, where it is negative. That's why I call sine table. Okay. But then to find the sign of your expression on each of the remaining interval, you can pick any sample point. For example, I can pick here 1. See that 1 is a number bigger than half. Plug it into your expression. That's a negative number. If it is negative, the value of expression in that interval is negative. The whole interval will become negative. You pick another sample point in the other interval, x equal to 0. You plug it in there. It's positive, yes? So that means that for every other value of x, this expression is going to be positive. Now, we are interested in 1 minus 2x being bigger than or equal to 0. It means that we are interested in positive part or 0. So that's why you have negative infinity. Let me just quickly write this one and finalize this. This is x is all in R for which x is less than half, or we are interested in this interval notation, which will give us this. Here, I am including half because square root of 0 is 0. It is allowed there. Any questions, any comments? Please ask the questions. I won't be able to check the chats. Alexander has a question there for the set notation. Can we write the section right of the line such that how you wrote it, or do we have to include that it cannot be 1 and 2? Well, the way, oh yes, that's I can do that one actually. I forgot that one. I can write this one as all x's in R for which x is not 2 and not 1. That's one way of writing. Please remember, if you have a question, raise your hand and ask the question. That way I don't need to go back to because I don't have any assistant here and I don't need to go back to the question. Anushka, please.
Could you explain the one where we use the union signs and the format? How do we write that?
Oh, the union thing here?
Mm-hmm.
So
Yeah.
you want to say this piece, and this piece. When you write interval, you cannot write sets as all in one interval. It sometimes, or most of the time, they are bunch of intervals. Yes. So here there are 3 intervals. Then you put union in between, meaning that that piece and this piece and that piece, all 3.
So, but then you wrote union 1 and 2, which means 1 and 2 will be included, right? But then it is not included.
No. See, 1 and 2 means what? Means all points in R which are between 1 and 2.
Okay.
Yes. If I wanted to include, it would be something like this. X bigger than or equal to.
Right.
Yeah.
Okay.
Yeah. You see, in the intervals, you write the interval in terms of the endpoints. So you go from this endpoint to that endpoint, from this endpoint to that endpoint. But to specifically say that if that endpoint is included or not, you have to use either round or close bracket.
Okay. So which means that in that union format, you wrote the 1 and 2 are not included.
Exactly. The way I wrote 1 and 2 is not included.
Okay. Thank you.
Daria, please.
Yeah, hi. I'm just wondering what makes a function considered to be irrational then?
Oh, irrational is this function. Sorry, that's a good question, actually, since I forgot to mention that. Irrational functions are the function which are some root of a polynomial. That's the format we call it irrational function.
Okay. And say like for the first example, say if you had like in like the polynomial on the bottom, say you had instead of x squared, it's x to like 0.4. Would that still be rational or would that be irrational then?
It's neither in that case.
Okay.
Like, yeah, you see, these are very specific types. If you combine them more than you're allowed, or not, you can do that. But if you do throw it different things, the name won't be polynomial anymore. For example, x to the power half plus 2 is not polynomial.
Right. Okay.
Yeah. Or
Okay.
if you have something like x plus 1 over 2x minus 1, this is not rational function anymore. This is division
Right.
of two rational functions.
Yeah. And would the same apply as well if, say in example 1, it was x squared minus 3 root x? Would that be neither then?
X squared, what was it? Sorry.
X squared minus 3 root x.
Yeah,
Like
yeah, I see it in the denominator.
Yeah.
This
Yeah. If you had something
this
like
is
that.
not
instead.
polynomial anymore. It's not
Okay.
polynomial. Yeah. This is allowed. You can have such a thing. Yes. But it's not polynomial. Polynomials are very specific when you have good powers of x, positive, non-negative powers of x multiplied to numbers and add.
Okay, great. Thank you.
You're welcome. I know I go very slow, but I think at this point of the course, it's very important. Please lower your hand, Anushka, if you don't have question, and then we go. Okay, so what about the range? I have been mentioning this. I will write it down. Range of a function. Well, remember, domain was all possible inputs. Range is all possible outputs of the function. So this is, we say, the set of all outputs of f. Okay, and if I want to write it in terms of the sets, this is all, all values of the function when you plug in all possible values of x, which in this case is all domain. So you plug in all the values of domain and see what are the possible values. Finding range is not always easy task to do. We will learn something next week when we learn, well, yes, when you learn inverse function this week in the units. But for now, what I want you to see is that if you have the graph of a function, say I have a function which is like this, the graph. Then you want to pick all possible values. Remember, the values of the function in the graph are noted by the y values. And as you see, all these guys are now in the range. But this point does not, this horizontal line does not intersect with the graph. So that means that this is not in the domain. In the range. That simply means that the range of this guy is all the values bigger than this line here. Simple thing here is that, for example, you can do lines. Yes, so if you have a line, it doesn't matter any line you have, say 2x plus 1. The graph of linear functions are line, and you can do it very simple. So when x is 0, this is 1, this is every line which is not horizontal line will intersect with all horizontal lines. So that means that in this case, range of non-horizontal line is always the whole real line. For parabola, the standard parabola, you know that it has this shape. And you see that the range of this guy is going from from 0, everything from 0 upward. That's how I write that. Now, if you want to find more things, then you have to start working a little bit harder. Try to sketch the graph of function. This is the most general thing at this point I can say. It will work more general than that. The trick, sometimes you learn, find the inverse and find the domain. But at this point, I just need to sketch this function. This is a quadratic. You can sketch that very easily. Willow, yes, please.
Sorry, would you mind scrolling up one more time? My computer wasn't. Thank you.
Do you want to take a screenshot of that, or?
Yeah, no, I thought I missed like another part of it, and I thought I had a question, but my question was answered after reading.
Okay, perfect. So in this case, I want to sketch the graph. Yes, remember the sketching graph of this guy is parabola. We learned some few things about the parabola. Well, we reviewed a few things last session. In one of the examples, I said that you can sketch the parabola by complete squaring the quadratic. So this is a quadratic polynomial, means that it is a polynomial of degree 2. You can complete a square. Completing a square of a quadratic means that you want to write it as x plus something to the power 2 plus something else. More general, there will be some constant also here. In this case, I don't have that because that's 1, so I won't be worried about that one. But this is called completing a score. Completing a score basically tells you how f can be obtained from the standard parabola or quadratic. Well, how do I find alpha and beta? See, if I know that there is such alpha and beta, I can go ahead and expand this. This will give me x squared. Remember, a plus b squared is a squared plus 2ab plus b squared. And then there's plus beta, yes? So I just write it down. Now, just match the corresponding coefficients. The coefficient of x squared is the same as the coefficient of x squared there. Coefficient of x, here's 2 alpha, that there is 3. The constant, here's alpha squared plus beta, here's 4. So you now see that 2 alpha must be equal to 3. And alpha squared plus beta must be equal to 4. This means that we have alpha 3/2. If I plug it in here, I see that 9 alpha squared 9/4 plus beta is equal to 4. Then that means that beta is 4 minus 9/4, which is 16 minus 9/4, and that is 7/4. What I showed here is that, okay, the function that we have can be written as x minus x plus 3/2 squared plus 7/4. Any questions, any comments so far? Well, then I can go a little bit further here and then say that, okay, nice. So I can sketch the graph of this guy by starting from the standard parabola and then turn it to this guy, which will be x plus 3/2 squared. I replace this x by x plus 3/2. And then shifting the second function vertically 7/4 units upward, and that will give me the third function, which is basically x plus 3/2 squared plus 7/4. Why this is important? Because, well, okay, so if I have the graph of this function, which is the standard parabola, I can go ahead and then copy and then paste it here. The second one, this guy here says that shift horizontally 3/2 units to the left. So that simply means that, oh, I take this one, and before this was 0, here was 0. Now this will go to the negative 3/2. Now I can do the last operation, which is shift vertical upward, copy and then paste. Oops, place, then paste. I can do the other one by shifting this guy 7/4, which is about 2 units somewhere here. This means that I am now somewhere here, which is 7/4. This is vertical shift 7/4 units upward. You can sketch the graph of that thing, but the important thing for me is that, look, range of f1 is anything which is bigger than 0, yes? Because the graph goes like that, so it goes from 1 to plus infinity. Then when I shift this guy horizontally, I'm not changing the range. While the values will be obtained in different points, but I'm not changing the whole set, because still the range is from, I did make a mistake here. This is not from 1, this is from 0 to plus infinity. And this guy's from, again, from 0 to plus infinity. Now I shifted it 7/4 units upward, so everything shifted 7/4 units up. This is just a way to sketch that function, but it will be always interesting to see how a graph transformation changes the range of the function. Sorry, I was trying to see if there is any question there. I will leave this one for you. Do it yourself. Just, I don't know what is the graph of the function, but it is the set of all possible values goes from -4 upward. Then here I have some translation, then some stretching a horizontal case, then some shrink on the vertical one. Then there is vertical shift. All these things you put together and see what happens when you change, when you apply one of these transformations. One key point is that horizontal transformations doesn't change the range. Vertical ones does change the range. The range. Okay, so I'll leave it for you. And is there any questions, any comments? Okay, then let's go to the last one. So then this is always the case in all mathematical construction objects. When you start with define some notions, you work with them, you study each one by itself, but then you try to find ways to generate new functions. So new objects of that kind. In the case of functions, This is that you can combine two functions in different ways and get new function. For example, you have two functions, you can add them. By adding, we mean this is a new function where first you evaluate the first function, then evaluate the second function and add them. You can subtract, you can multiply, you can divide. All this works. These operations are called combination of functions. We have also one new way, one different way. It's called composition of functions. Well, this is very nice with the picture of each function is a machine. So if you have a function g, you put in x as an input, it spits out an output gx. Now you take that gx and plug it into the second function. This is a machine. If that gx is in the input, in the domain of f, the outcome will be f, the output of f, evaluated at g of x. In other words, you compose these two guys and you define the new machine, you put it in a new box. What people now can see is that if you put in x, it will spit out f evaluated at gx. This is composition of two functions. FOG at x means f evaluated at the output of g. Well, we have some examples here for you. For example, h is given by this combination. So then if you're looking for h at 1, this is nothing but f at 1 plus 3 times g at 1. It means that you evaluate, you multiply the second one by 3 and then get it out. So this means that you have 1 squared plus 3 times 1 plus 4 plus 3 times 2 times 1 minus 1 over 1 plus 2. Whatever the number is, but that's how it is defined. FOG, you can find the function itself. This is f evaluated at gx. It means that you take gx, whatever gx is, and put it as input of f. So f, what does f do? F squares the input, multiplies the input by 3, and adds these two and add them to 4. So now the input is gx, so it will square gx, then multiply gx by 3, and then add that to 4. And this means what? This means that 2x minus 1 over x plus 2 squared plus 3 times 2x minus 1 over x plus 2 plus 4. If we are interested in finding h at 0, it means that we are interested in finding FOG at 0, which is the same thing as g at 0. But g at 0, we have a formula for that. 2 times 0 minus 1, 0 plus 2. This is f at negative 1 over 2. And then negative 1 over 2, you have to square negative 1 over 2, multiply negative 1 over 2 by 3, and add these two and add 4 to that. Well, you can evaluate that number there yourself. FOGOG, this is, I will just write this one and leave it for you to complete. This is basically this. You have the first plug in gx into g itself, and this means simply 2 times gx minus 1 and gx plus 2. And then you can plug it in back gx, which is 2 times 2x minus 1 over x plus 2 minus 1. This is 2x minus 1, x plus 2 plus 2. And then you take all these things, evaluate f at. So I will leave that one for you. How about this? I don't need to find the formula for that. I can just go ahead. H at 0 is g o f at 0 plus 0. X is the function which sends x to x. It's called identity function sometimes. And this means that g at f at 0 plus 0, but g at 0, f at 0 is 0 squared plus 3 times 0 plus 4, which is g at 4, and g at 4 is 2 times 4 minus 1 divided by 4 plus 2. That's the value. I'll leave it like that. So you have to be able to work with these combination compositions, and then we will talk about these ones later in more, well, whenever we have like differentiation specifically, sometimes limits and so on. Fabiha, yes, please.
I just wanted to ask if it was like for every step, do you have to always include f of the like worked out process for every step?
Can you please specifically let me just go, for example, on this one.
For the third example,
Oh, I see. Yes.
f of in brackets in the second step, f of
Yeah.
g.
You see here, oh, where's my pen? Here, I have not yet applied f. What I mean by that is that, let me just push this one down. I have not yet applied f, meaning that while I haven't used from going this to that, I haven't used the formula for f. I could have gone the other way. So you don't like f, I can go like this. Okay, the input is g evaluated at gx. F is square the input 3 times the input plus 1. You could have gone this way as well.
Oh, okay.
Yeah. Here, since I'm not using the formula, applied the formula for f, that's why I have to take it with me. No.
Okay. Thank you.
We are at the end of this. Let me just pause or stop recording.